Hello everyone, my name is Emmanuel. I would like to talk to you today about our research entitled Mass Transport Modeling of Total Organic Carbon in Groundwater to determine the location of petroleum fuel pollutant sources in the area of Jalagrang, Yogyakarta City, Indonesia. This presentation will start with introductions and objectives, methodology, and the last part is results and conclusions. This research is located at Gedong District, Yogyakarta City. In the year between 2000 to 2001, groundwater in the dock wells of residents around Yogyakarta train station was contaminated by diesel fuel, and it was concluded at that time due to a leak in the fuel storage tank. In this map, you can see the pollutant source marked with a red rectangle and indicated by a red arrow. We can see one of the photos from my documentation in the research area shows light non-aqueous phase liquids such as fuel has a lower density than water, so the LNAPL will float above groundwater. The spread of hydrocarbon contamination in this area was conducted by Setyaningsi in 2010 and Wijaya in 2015. It was found there is no significant change in the contaminant plume. Theoretically, the length of the plume condition, which tends to be constant, shows a balance between the attenuation process and the continuation of pollutant spilling. Objective of this study to simulate whether of source of hydrocarbon pollutants in the study area is a point source or an area source. And the limitation of this study, the oxide level are used to represent hydrocarbon fuel pollutants. The methodology begins with collecting primary and secondary data. After these data are collected, we can perform groundwater flow modeling in the ModFlow software. If the model has not been calibrated, we need to check the data again. If the model has been calibrated, we can continue to create a groundwater pollution flow model. If we have not found the calibration limit below 10%, we have to check the mass transfer data. If the model has an error below 10%, it can be stated that the model has been calibrated, so the model can be used for interpretation. The Chode and Winongo River observations data are shown in this table list. In the table are as follows: site observations, river stage, thickness of water, etc. And points observations are shown by red circles on the map. The groundwater level obtained from measurements of the elevation of shallow wells in the study area shown by 53 green circles on the map. Next slide is boundary conditions. The research area discretized into 60 power 40 grid cells. Vertically, this model is only divided into two layers. Layer 1 represents unconfined aquifer and layer 2 represents continuous layer of clay. There is the value of hydraulic conductivity in both layer and vertical boundary geometries of both layer above sea level. Groundwater flow model simulations are carried out in steady state, and groundwater flow model calibrations are based on data from 53 groundwater level elevations. The recharge boundary in the study area is 500 mm per year. No flow boundary is placed on the western and eastern boundaries of the model as inactive cells. The constant head boundary conditions in the model are placed on the northern and southern boundaries of the model area. Groundwater samplings and analysis. Groundwater samples are taken and collected using dark glass bottles and stored in an icebox, which functions to keep groundwater samples associated with volatile pollutants below room temperatures. The tool used to analyze TOC content was the Vario TOC Analyzer. This tool provides measurements results in the form of TOC content in milligram per liter units. The following table shows the results of analysis of groundwater samples. The map shows the distribution of groundwater samples well that have been analyzed, which are indicated by red star points. In the mass transportation model, we add the input data shown in this slide as follows: the form of pollutant source, species per meter or decay rate, bulk density, dispersion, initial concentration, time discretization, and particle tracking. The mass transportation modeling calibration with TOC as its parameter is carried out only for 8,030 days since the fuel storage tank leak occurred. The mass transportation model running was carried out in two cases. First, the source of pollutant was determined to be a point source. Second case, the source of pollution is the entire area of the train maintenance facility or an area source. The left map shows the conceptual model from all data were collected previously, while the map on the right slide shows the discretization of the model in the map previously described. The groundwater flow model calibration is obtained by zoning the hydraulic conductivity parameters of layer 1 into zones of the distribution of hydraulic conductivity as shown in this figure, while layer 2 does not change in the value of hydraulic conductivity zoning. The results of the calibrated steady groundwater modeling with the smallest error are shown in the right figure. The groundwater flow is generally divided into three flow directions, namely to the south, to the west feeding the Winong River, and to the east feeding the Choda River. The groundwater flow patterns towards the rivers shows that the two rivers are of the gaining stream type that feeding by the groundwater. Next slide. As explained in the methodology, the case 1 mass transportation model running is carried out by entering a pollutant source, a point source, shown by a red rectangle on the left map, with a TOC concentration of 300 mg per liter at the time interval of 0 to 180 days leaking. After the 180 days to 20 years later, the pollutant source is not activated. In this case 1, it's clear that the plume of contamination does not affect several dark wells that are indicated to be contaminated with are analyzed either directly or in the laboratory and have a distinct fuel odor, turbidity, and have high TOC levels such as SG8, SG9, SG10, SG23, SG28, SG29, SG30, SG31, and SG34 wells. So we need a model that fits a small error to describe the distribution of groundwater pollution using the concept of case 2. The pollutant source is should not only come from the leak of the tank or point source, but other sources. The source of fuel pollutants has been the source area as shown by red areas in the left figure, and we have error below 10%. So the source of actual plume of pollution based on the TOC content in groundwater only match if the source of pollutant were determined as a whole area of the drain maintenance, not from a point source. Thank you for your attention. Terima kasih.